Okay, so let's summarize what we know about the osculating circle. Its center is defined by the vector rho n plus r, where rho is your v squared over centripetal acceleration, v being the magnitude of your velocity vector, your derivative of the r vector, and acceleration being the perpendicular component of your acceleration, component perpendicular to your velocity, all easily calculated. So we know what the center is, and there's the expression for it. We postulate a point x, y, z that's on the circle. So if x, y, z is on the circle, then what can we say about it? Well, we can say that the vector from here to here has to have magnitude equal to the radius of the circle. Now, rho, remember, was the radius of the circle, so that the magnitude of this vector has to be rho. Now, how would you write this vector? Well, you would write it as Pn plus r. Remember, Pn plus r is a combination of two vectors that get you from the origin to the center. And of course, x, y, z is a set of coordinates relative to the origin and the coordinate system and so forth. So vector from the origin to x, y, z would be here. So if you regard the vector that defines the x, y, z point as p, then p minus the vector rho n plus r, well, it's going to be what you have here, okay? So again, from the origin, rho n plus r, and then this vector gets you to the vector xi plus yj plus zk. Let's be clear about one thing. Now we've got an x of t, a y of t, and a z of t. The x, y, and z functions that define your curve in terms of the parameter t. This is just a point x, y, z. There's no t dependence here. So it's just some point x, y, z on the circle. Okay? Now, the point x, y, z is on the circle, provided this vector has magnitude 1, has magnitude rho. So we have this condition for the point to be on the circle, and the other condition for the point to be on the circle, because of course, if we only had this condition, we'd have all points that are distance rho from this point, so we'd have a whole sphere. We only have the circle. The sphere might oscillate with the curve at the given point, but we're not interested in that. We're interested in the circle. And the circle has to be in the plane of motion, which is in the plane of your unit tangent, unit normal vector, therefore has to be perpendicular to the binormal. Meaning that this vector, again, has to be perpendicular to the binormal, meaning its dot product with the binormal is 0. So you have these two conditions that define your circle, and you put these together to get the equation of the circle. Okay? Now, I've written some stuff down here that turned out to be kind of unnecessary. And I've reiterated that P is a point x, y, z. R is the vector x of t, y of t, z of t. Or r of t, x of ti, and so forth. This is the vector from the origin to the point on the curve. This is the point on the circle. Again, the x, y, z here don't have t's on them. Okay, so rho, again, is v squared over a perpendicular, and we calculate that pretty easily. V squared is the square of the magnitude of the velocity. The magnitude of the velocity, well, the velocity is x prime I plus x prime of ti plus y prime of tj plus z prime of tk, and we know that very well. So that the magnitude of the velocity is the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. Okay? And I just write that as x prime squared plus y prime squared plus z prime squared. The t is implicit, and this is distinguished from the x, y, z here because these are just points, they aren't moving, they don't have derivatives, but these do. So you can put the t in here. Maybe I should have done that in the first place, but let's go ahead and put the t dependence in here. This chalk is not being very cooperative. Okay, so there we go. And now it's all messed up, but you see that it's just the square of the square root of the sums of the squares of the components of your v of t vector, and that's very straightforward. Your a perpendicular is just your a minus a parallel vector, and a perpendicular is just the magnitude of that vector. So this is easy to calculate. B is your unit tangent times unit normal, that's easy to calculate. So all easily, if maybe a little bit tediously calculated from your r of t vector. You end up with kind of a rotated analog of the equation of a circle in the xy plane, but you're restricting it to a plane, so there's a complication that comes up there that I'm not going to talk about right now, because I just want you to see the details of how this comes about. Once you see all this, then it becomes fairly easy to put together. Now this is going to have x squared, y squared, and z squared terms. It's going to have xy, possibly xz, and yz terms, second order terms. But it's not going to be just a quadric form, because a quadric form is going to give you a quadric surface, and a circle is not a surface. Okay, so you have to worry a little bit about that. Okay, anyhow, that's where you go with this. Once you understand this scheme, you can calculate all this, and next time we'll talk about how we put it together and what the equation actually looks like.